Hi, everyone, and welcome to this SpudSmart webinar on stress factors and management practices of sugar end disorder and stem end chip defect. My name is Carrie Belanger, and I'm the editor of SpudSmart Magazine and SpudSmart.com, and today I'll be acting as your moderator. Sugar ends and stem end chip defect are tuber disorders affecting product quality of processing and chipping potatoes. The environmental stresses causing the disorders occur during the growing season, but tubers appear asymptomatic until harvest or later in storage. During this webinar, two industry experts will discuss stress factors and management practices for these disorders. First, I'd like to thank our sponsors, McCain Foods and BASF, for their support. I'd also like to take care of a few housekeeping items at this time. This webinar is being recorded and will be made available on SpudSmart.com following the event. And for audio quality purposes, all microphones have been muted with the exception of the speakers, but we do welcome your input. If you have a question or comment, please share it in the chat box. Today we have two guest speakers. Dr. Mike Thornton is a professor of plant science at the University of Idaho, and Dr. Paul Bethke is a scientist with the USDA Agricultural Research Service and an associate professor at the University of Wisconsin. On our agenda today is to review sugar end disorder, discuss the key stress factors causing sugar end or jelly end rot development, discuss management practices to help reduce sugar end disorder, review stem end chip defect, discuss the causes of stem end chip defect, discuss the varietal differences in resistance to defect formation, and finally discuss the potential for biotech potatoes to reduce the severity of stem end chip defects and sugar end defects. Please type your questions or your comments into the chat box at any time during the webinar, also indicating to whom the question or comment is directed. At the end of the complete slide presentation, there will be an opportunity for each guest speaker to answer the questions posed in the chat box. Mike Thornton is a professor of plant science at the University of Idaho. He specializes in plant physiology, potato and onion agronomy, and handling and storage management. Mike conducts applied research to resolve production issues identified by the potato and onion industries. Please take it away, Mike.
Thank you, Carrie. Appreciate the nice introduction, and I'll move right into my topic, which is factors that cause sugar ends in potatoes. And this is actually a disorder that was fairly important and still is in Southwest Idaho, where I work for the University of Idaho. In the 1980s, it actually led to quite a reduction in the acreage in this region because they were having problems with sugar ends. And that prompted a lot of research as to what causes sugar ends. And I'll be citing some of that research today. So what is a sugar end? Well, it's a physiological disorder. And those are characterized by being associated with a stress, usually something in the environment or associated with management. But what it's not associated with is a pathogen or a pest. And that's what separates disorders from diseases. This particular disorder, sugar ends, is associated with elevated reducing sugars and reduced starch in the tuber. And if you look at the picture on the bottom of the slide, you will see a good example of sugar ends where when you fry them, those reducing sugars turn dark on one end of the potato. And as I said, sometimes it's associated with a reduction in the starch. And in extreme cases, you'll actually have a clearing or translucent appearance of that stem end where the starch is low. And that's where I'll talk about a couple other names for this disorder, but it's associated with that clearing of the starch where we get names like translucent end or glassy end. As I said, it causes one end of the tuber to fry darker than the other. And most commonly, that's the stem end of the tuber. This is the oldest end of the tuber, first formed. It's most susceptible to developing sugar ends. There is a kind of sugar end disorder associated with immaturity that is in the bud end or the opposite end of the potato, but it's not very common. And I'm going to talk mostly today about the sugar end that it develops in the stem end. As I said, there's a couple other terminologies you'll hear related to this defect. The first two, glassy end and translucent end, are associated with this reduction in starch on one end of the potato, mainly the stem end. And if you cut them open, you will actually see where those cells have kind of cleared out and they look glassy or translucent, hence the name. Dark end is just another terminology for the appearance of those potatoes when you fry them, where one end tends to darken due to the high reducing sugars. Jelly ends are actually an extreme form of sugar ends. So if you look at the picture at the bottom of the slide, you see a potato on the far left side that is kind of a slightly pointed stem end, indicating that maybe the tuber went under some stress early in the growing season. May or may not have slightly elevated sugars on that stem end. But as we go to the right, we see more and more deformation, a more pointed stem end for the second to the left tuber. And then we get into the one that's second from the right, where you can see some collapse of the cells at the top of that tuber. And that's because the starch has completely gone out of that tissue and it's basically degraded into a collapsed cell, and you can see the collapse and the shrinking of that stem end tissue. The picture or the tuber on the very far left is the most extreme example of jelly ends, where that tissue, because of the lack of starch and the high sugars, basically degrades the cells so much that it collapses into this form, and sometimes that collapsed tissue will even slough off and leave the rest of the tuber. So this is the extreme form of jelly ends. We're going to talk a lot about sugars today, and I just wanted to point out that sugars are necessary. It is how the plant captures the energy in sunlight and stores it through this process called photosynthesis. And so the sugars are produced in the leaves, transported down to the tubers through the vascular system of the potato plant in the form of sucrose, which you see in the middle of this potato figure that I'm showing you. Under normal situations, that sucrose is transformed into starch. That is the more long-term storage form of energy in a potato tuber. That's what we want to happen. But when the crop undergoes stress, this conversion from sucrose to starch is affected. It's less efficient. And so some of that sucrose remains in that form and can be broken down into glucose and fructose, which are the reducing sugars that cause this darkening when the product is fried. So it's really this conversion over to glucose and fructose during growth and the resulting high reducing sugars that causes the development of sugar ends. So what causes this disruption of carbohydrate and energy use in the potato and results in the physiological disorder sugar ends? Well, there's a couple of key factors that we've been able to identify. One of them is soil temperature. What I'm showing you here is a graph of mean soil temperatures or average daily soil temperatures from the 1st of July through the 30th of July for a production region. This one happens to be in the Midwest United States, and 2 separate years. So the solid line is 2003, the dashed line is 2004. And what you'll notice is that 2003 was a significantly warmer year. The soil temperature was in the mid to high 70s for a good portion of this period through July and August. And that was the year when they had a very high incidence of sugar ends. You contrast that to 2004, a cooler season, where there were only short periods where soil temperatures got above the mid 70s. And in that year, the incidence of sugar ends was relatively low. So we know from this kind of information and other studies that have been done that soil temperature, and particularly when soil temperatures get above the mid-70s, this sugar to starch conversion doesn't occur as well, and that's when we have this buildup of sugars in one end of the potato. Luckily, most of us know that the air temperatures are often above mid-70s during the growing season, but the soil temperature down where the tubers form, and usually 4 inches deep or deeper, is often cooler than that. And that's due to shading from the leaves and also evaporation of water from the soil surface that actually cools the soil. So even when we have very hot days, if we have good soil moisture conditions, we have good canopy cover and vine development, soil temperatures can remain below this kind of critical level of mid-70s and keep us from having physiological disorders associated with sugar ants. A second factor that's really important in sugar ant development is water stress. This is some of that work that was done in the 80s by a colleague of mine, Clint Schock at Oregon State University. And Clint showed the impact of a single water stress at various levels of available soil moisture. So on the bottom, you have available soil moisture going from 100% on the left to 35% at the right. So basically, field capacity is 100% available soil moisture. 35% is almost the permanent wilting point, so very dry soil. Our general recommendation for potato production is to keep the soil moisture above 65% available throughout the season. And you can see when we got drier than that in the red line in 1991, we start to see a spike in sugar ants. If we allow the soil to go drier down to 45 or 35%, the incidence of sugar ants goes up, which brings up a really important point. The more severe the stress, the higher the incidence of a physiological disorder like sugar ants we see. You also notice in the green line in 1992, we see the same exact pattern when we get below that threshold of 65% available soil moisture, where we're seeing that white bar that I've got there for the threshold, we see an increase in sugar ants. But notice it's much higher than we saw in 1991, and that's reflecting the importance of environmental conditions. 92 was a hotter season, so the combination of a very hot climate with water stress was more damaging in 1992 compared to 1991, where we had cooler conditions. So if it's not very hot, we can have a little bit of water stress and not see a big spike in sugar ants. But if it's hot out there during a season and we have water stress in addition to heat stress, then we get a very high incidence of this disorder. So water stress and heat stress are definitely tied together in terms of how they impact this disorder. And we also need to note that the timing of that stress and when it occurs is really critical. We know that potatoes are most sensitive to stress that causes sugar ants during early tuber development. So the time from first tuber initiation, when the ends of the stolons first begin to swell, up until the time when the tubers are about the size of a hen egg or slightly smaller. And if we get stressed during that period, we will often get very characteristic tuber shapes that you can see on the top line of the graph or figure that I'm showing you, where we have a narrowed or pointed stem end, and then the rest of the tuber, if the stress is relieved, forms normally. This is the period, that early stress, where if it occurs, we tend to see the highest incidence of sugar ants. Once we get past mid-season, and particularly into late season, if we have stress, we can get tuber malformation, like the dumbbells you see in the middle, or the pointed bud end you see with late stress, but we don't have as big issues with sugar-related disorders with that late season stress as we do with early season stress. Third factor in sugar ant development is plant maturity. And this is nice work done by a colleague at Washington State University, Rick Knowles, where he took data from one of the processors in the Columbia Basin, and they just looked at one variety, Ranger Russet, and when it was harvested. So what I have across the bottom is days after planting until that field was harvested. And on the left-hand side, on the y-axis, is the percent of sugar ends. And what you see is, as you push that crop later and later, gets more mature, we get a higher incidence of sugar ends. And basically what Rick showed was that the crop, in this case Ranger russet, matures at between about 145 to 155 days after planting in the Columbia Basin. If you allow that crop to sit in the field longer, it tends to start maturing, starts senescing, and those tubers lay in the soil under hot conditions. The soil temperature is fluctuating. It's getting into that region of mid 70s that I talked about. And this over maturity process tends to increase our incidence of sugar ends. So ideally, if we want to minimize these sugar-related disorders, we would harvest the crop when it's physiologically mature. And that's defined as the point of maximum yield, maximum starch content, and minimum sugars. Past that point, then we start to see a spike in sugars and sugar-related disorders. The fourth factor associated with sugar ends is exposure to cold. And this cold exposure can occur in the field if you're in a region where harvest time temperatures get below, and particularly below about 45 degrees Fahrenheit, or it can occur after you take the crop into storage, as I illustrate here. So again, some data from Rick Knowles at Washington State University, looking at a crop of Ranger russet. So October 22nd is the harvest date. And what I'm showing you on the y-axis is the reducing sugar levels. And what he's done is separated the stem end sugars in the dark line and the bud end sugars in the lighter colored line. And notice right at harvest, we don't see a big difference because these potatoes have not yet been exposed to cold. But as we get them into storage and start ramping down to the holding temperature, which we get to on November 25th, so 45 days into storage, now we see that the sugar levels in the bud end, or the stem end, have spiked considerably more than they have in the bud end. And it's this difference in reducing sugar levels when we fry that crop that's associated with this gradient of color in that French fry that I'm showing you here. And we define that as a sugar end, something that's not desirable by the people that purchase these French fries. So it's one of those disorders, as Carrie pointed out in the introduction, like many of these physiological disorders, where the stress can occur very early in the season, but we really don't see the symptoms until we get that crop exposed to cold, either in the field or, as I'm showing you in this case, in storage. One thing I will point out, Paul's going to talk about in the stem end defect, where sometimes that defect will get better in storage. In this particular case, you can see that the sugars change a little bit with time in storage and start to drop, but we still have this big differential between stem and bud end. And so basically, I've never seen sugar ends really get better in storage. They only tend to stay the same or get worse. So now that we've described this disorder and kind of the factors that cause it, what do we do about it? How do we manage it? Well, as with most physiological disorders, there's an environmental component, which we can't really do much about. The temperatures are what they are. We have a genetic component based on the cultivar or variety we choose to grow. And then we have the management component. So let's start by just showing how big an impact variety choice can have on this particular disorder. So I'm showing you again sugar end incidence on the left side, the y-axis, and a selection of 6 processing russet varieties, some that are grown fairly widely, like Clearwater and Umatilla and Burbank, and some that are not, like Alpine and Premier. But what you see is the incidence of sugar ends at 2 different irrigation levels. So you can see there's a treatment with 50 centimeters of water applied during the season and one with 38. The difference in irrigation isn't that big. What I really want you to focus on is the relative susceptibility of the varieties. And you can see that Russet Burbank, under these particular years from 2012, had an average of about 20% sugar end incidence regardless of how we irrigated it. Again, pointing out the importance of soil temperature because these were hot years, and even when we irrigated well, we still had a high incidence of sugar ends. Compare that to the other 5 newer varieties that have pretty good stress resistance, and you can see in those we have a 4 to 5-fold less incidence of sugar ends in those varieties compared to what we see in russet Burbank. And it really points out that russet Burbank, when you grow it under good growing conditions, good fertilizer, good water, and a cool climate, it has very good quality. But when it's stressed, it becomes the poster child for physiological disorders. And one of those it's very susceptible to is this sugar end disorder. So variety choice can have a huge impact on how susceptible the crop is to the development of sugar ends. Unfortunately, like with environment, we always don't get a chance or a choice in the variety that we choose. We might have a contract that specifies we have to grow a specific variety for the company that's buying our potatoes. And so we really need to now talk about management. What can we do from a management standpoint to minimize the incidence of this disorder? And there's really 3 kind of areas I'm going to talk about, and those are root development, vine development, and vine senescence. But let's start by talking about root development and how that can contribute either to resistance to sugar end or development of sugar ends. Basically, what I'm showing you now is a schematic of what a potato root system looks like when it's healthy. And you can see that it is primarily concentrated in the top foot of soil. Some people say about 70% of the root system is in the top 12 to 18 inches, and you can see that in this figure. And once you get below that, the root system is pretty sparse. So compared to other crops that you might be familiar with, like wheat, potatoes are shallow rooted and they're fairly sparsely rooted. So anything we do to disrupt that root development is bad for the plant's ability to take up water, to cool through evaporative cooling, and to resist stress. And so what I've shown you here are 2 common ones. If you have cropping systems or tillage practices that result in compaction, you can restrict the depth that root system will develop. And even though there's not a lot of roots down below 18 inches, those roots are important for extracting that deep moisture. Likewise, if you are in a system where you tend to go in after emergence and cultivate the crop, say with something like a basin tillage type of implement, if that crop is very much immersed and has much of a root system, you can go in through there and prune part of that root system and end up with a less extensive root system than you should have. To the side on the right, I also mentioned a couple others factors that can impact root health and root development, and those are pathogens, and particularly the ones associated with Rhizoctonia and Verticillium can come in mid to late season and start reducing the amount of roots that are under the crop, as well as nematodes that are feeding on the root system can reduce the ability of that root system to take up moisture from the soil. So any of that is bad for resistance to stress and resistance to development of sugar ends. The second factor that I'm going to talk about is vine development. I'm going to kind of lump either very poor vine development or excess vine development together because they both cause a problem. As I said earlier, shading is one of the key ways that we keep soils cool in a potato crop. And so anything that restricts the development of the canopy, the vine development, and prevents shading so that we don't have solar heating of the soil is likely to increase our incidence of sugar ends. So I'm showing you a picture here of a field that's got a very erratic stand. We've got some missing plants. We've got some very weak plants. And I think you can imagine a couple weeks from this, if you're starting into that early phase of tuber development and you haven't covered the rows and gotten the shading that you need, the soil temperatures will be hotter in portions of the field where the vine development is also poor. So getting a good stand, getting a good formation of leaves to shade the soil is really critical, but we can also overdo it, particularly with nitrogen fertilizer. We know that if we want to get a big plant, one of the ways to do that is to really push the crop with high nitrogen. And that's a good way to shade the soil, but once you get 100% shading of the ground, it doesn't do you any good to have even a bigger canopy, a bigger amount of leaves than that, because all these leaves are evaporating water. They're basically determining what the water demand is by the crop. And not more nitrogen than you need for 100% ground cover just makes the crop want and need more and more water to cool itself. But adding more nitrogen doesn't do much to root development. So you can get it into a situation where vine and root development is basically out of imbalance, and you have more demand by the plant than the root system can supply, even when the soil moisture is adequate. So excess vine development really can lead to water stress in conditions where you think the soil is adequately irrigated. And then finally, early vine senescence. As I said, overmaturity and having potatoes sit under dead vines with the soil temperature fluctuating up and down, and particularly if you have a warm fall, can lead to an increase in sugar-related disorders. So anything that causes a rapid decline in canopy at the end of the season, so things like early die, which is impacted by fumigation and choice of rotation crops and how long you rotate, all those kind of things that lead to the decline of the canopy at the end of the season can increase your incidence of sugar ends. With that, I would just summarize the key points of what I've gone over by indicating that, sugars are required for normal plant growth and development, but stress causes a change in how the plant deals with those sugars, and particularly how it puts them into starch instead of reducing sugars. If we want to manage to reduce sugar ends, the first thing we do is look at our variety choice, but beyond that, any of our cultural practices that impact root development, canopy development, or late season vine health are going to affect our ability to reduce the incidence of sugar ends. So with that, Carrie, I will turn it back over to you for the second part of this presentation.
Well, thank you so much, Mike, for your presentation. Our next guest is Dr. Paul Bethke. Paul is a scientist with the USDA Agricultural Research Service and an associate professor at the University of Wisconsin. His research focuses on how genotype and environmental conditions during growth and storage influence the quality of potatoes. So, Paul, the floor is yours.
Thank you, Carrie. I'm going to talk about stem and chip defect, and as Mike has already alluded to, there are a lot of similarities between stem and chip defect and sugar end defect. So what is stem and chip defect? In the illustration here, we see a couple of chips that have stem and chip defects. It's a darkening at a characteristic position at the stem end of the tuber, often associated with the vasculature. It occurs quite erratically over years and locations, and that's made it difficult to study. And there's a very strong varietal dependence, as we'll talk about in just a minute. So these are all some chips with varying amounts of stem and chip defect. In some cases, such as the chip on the upper left, there's nothing really to look at. It's a beautiful chip. 2 chips over to the right is one with a fairly severe defect, the sort of thing that probably wouldn't make it into a chip bag and would make a chip processor quite unhappy. So we try to capture this range of defects numerically, as illustrated here. So we've established a rating scale for stem and chip defects that runs from 0, meaning no discoloration, 1, just discoloration of the vasculature, and then increasing amounts of darkness, basically going farther and farther and farther into the chip. And we chose this in terms of, distance into the chip rather than darkness, although the two are often correlated, because that reflects how the chips might be processed. That is, if If the defect area doesn't extend too far into the chip, you might be able to peel it off. If it's too far in, it's not worth doing the extra peeling, and it's because it's economically disadvantageous. So our scale runs from 0 to 5, and I'll ask you to remember that. 5 is bad, 0 is good, because we'll look at some data later on that compares these numbers. Okay, so this slide illustrates really the heartbreak of stem end chip defect. Often at harvest, or even a little bit after harvest, when you do a chip fry of a load of potatoes, it can look pretty good. So on the left, this at harvest sample, there's one chip sort of near the lower right corner that clearly has a defect, and there's a couple of others that aren't perfect, but overall, it's a pretty nice looking load. And then 1 month later, same sample, looks like the set on the right, where most of the chips have defects that are going to cause a problem for a chip processor and then, by extension, to the grower. So that's the heartbreak of stem end chip defect, and that's one of the reasons it's been of a great deal of concern to the chip potato industry. So what do we know about what causes this? What do we know about what we can do about it? So Mike alluded to this. Stem end chip defect, unlike sugar end defects, can actually get better in storage. So these are some data that we generated for the variety Snowden, which is a storage variety that's grown, has been grown widely over the upper Midwest of the U.S. So I'm looking at, on the y-axis here, the average stem end chip defect score. So 0 is good, 4 is really bad. And on the x-axis, time after harvest in months. So coming in, a lot of potatoes that's experienced this low environmental stress, the solid symbols on the bottom, has an average defect score of about 1, and one that's had a high environmental stress, in this case a heat stress, has a score of about 1.5. Both of those numbers are just fine. The chips would look pretty good. And then a month later, they've actually both gotten worse. The low environmental stress and the high environmental stress have both gone up in their average stem end chip defect score. And this seems to be something that we see with virtually every variety we've looked at. There's a slight increase about a month or two after harvest. For the high environmental stress lot, the increase has been much, much larger than for the low environmental stress lot. And so now our average defect score is 3.5, right? Anything over a 3 or so is problematic in terms of chips that can be scored as defects. But then what happens? And a month later, and we're now at 2 months, and there's been an improvement in that lot. And by 3 months, it's gone down even further. Still not as good as the low stress lot, but it's improving. And with enough time, it may be a completely acceptable lot. So this is one of the things about stem end chip defect. If you can store the chips under very good conditions, they sometimes will improve over time enough that a problem can be minimized or reduced at least. But not always. If the defects are very severe to begin with, you may not have enough time for them to get to the acceptable point. And for some varieties, we've seen some sort of erratic behavior with longer term storage. And Lamoka is one of those. That's illustrated here, the same sort of setup, average stem end chip defect score on the y-axis and time after harvest for a lot that's had low stress and high stress. And it looks like it's doing the same thing as Snowden, although up to about 2 months. And then there's a blip upward again. And it shows up both in the low environmental stress lot and the high stress lot. And what's that all about? And it's where averages sometimes don't tell the whole story. So most of the chips in a sample are continuing to get better under this condition, going from 2 to 3 months. But a few have gotten much worse. So they have actually fairly severe defects. And we've seen this several times with Lamoka, that things look pretty good, and then some of the chips all of a sudden start to look really bad. So as Mike said, stem end chip defect can get better in storage. It's not a guarantee, and we at least know that there are some varieties that seem a little more problematic in that regard than others. Okay, let's go on to the next one. So what causes stem and chip defect? As much as we know, and there hasn't been as much research on this as there has been for sugar end defect, many of the same things that cause sugar ends contribute to stem end chip defect. Heat stress is the one that we know to be probably the biggest cause. We've got some data showing that verticillium is associated with higher stem end defects. Defoliation, our growers have mentioned several instances where a defoliation event has led to very high incidence of stem and chip defects. Defoliation from a particularly bad infestation with insects or from hail. So this, I think, is really reflecting a grand disturbance in carbohydrate metabolism, the regrowth and the starving of the tubers for energy. But that's a bit of my speculation. What we do know is that heat is the biggest one. We have no data so far that suggests that water stress is a contributor, although that's largely because we don't have any data looking at that one way or another. So let me show you how we experimentally can trigger stem and chip defects. This is a air temperature that we use in a controlled environment setup where we grow plants for about 100 days under optimal conditions, bright light, 22-degree days, 18-degree nights. And then approximately 100 days after planting, we impose a stress period, a heat stress period, where the daytime temperature is 35 degrees and the nighttime temperature is 29. Notice that this is substantially offset in time from the stress period that Mike was talking about as being most crucial for sugar end defects. It's not early tuber bulking. It's actually much later than that. It's the time of year, about the first week of August or so, in our production area where we might expect to have some really hot days. So we impose this fairly brutal stress period for a week, bring the plants then back to under controlled conditions, and we'll harvest the tubers typically 1 to 2 months later, whenever the plants want to senesce, and then look at them at the chips at harvest 1, 2, and 3 months after that. So that's our experimental system. And this is what you see, right? Without heat stress, you have beautiful chips 1 month after harvest. That's where these chips were made. And with heat stress, you have beautiful defects, right? So heat stress is actually one of the biggest contributors to defect formation. It's also problematic in that there's not a lot you can do about heat stress. The duration of the heat stress actually does seem to matter. Stem and chip defects get worse as heat stress duration increased, at least experimentally. So here's some data looking at chips scored for the defects from 0 to 5, where 0 is good and 5 is bad. Controls at harvest and through 12, and then we're looking only at severe defects. So in this case, percentage of chips with a score of 3 or greater, things that a chip processor might score as a defect. In the controls from harvest to 12 weeks after harvest, we see no defects with scores greater than 3. 3 days long heat stress period, essentially no defects, 1 chip out of 20 at 4 weeks. And by the time you get to 7 days or 14 days, now you're seeing substantially increased number of defect chips. So increased duration, the greater the stress, the greater the problem with defects. This is again similar to what Mike had said about sugar end defects. We have some field data from grower fields that sort of supports this idea. Here we're looking at graphs for 2 varieties, Lamoka and Manistee, 2 chipping potato varieties. The y-axis is again looking at average stem and chip defect score from non-existent at 0 up to, in this case, 3. And then the y-axis is the number of nights over the growing season where the air temperature is 68 degrees Fahrenheit or greater, 68 degrees Fahrenheit for my friends in Canada is 20 degrees Celsius. So the blue circles, these are grower fields throughout the upper Midwest and the high plains states. It's actually over a very wide geographic distribution and several years. The blue circles are data that actually follow a fairly nice trend line, where the greater the number of warm nights, the higher the average stem and chip defect score from a field would be. Each of these circles is an individual field. The orange squares are fields that don't fit the pattern, and they're always above the trend line. So warm nights seem to be a major contributor, but other things can go wrong too and bump up your average stem and chip defect score considerably. So it's a multifaceted cause, temperature being one of those causes. The figure also illustrates one of the things about variety. You can see, regardless of the number of warm nights, we're seeing that the trend is lower for the variety Manistee than for Lamoka. These are the sort of differences that we can think about in terms of trying to manage stem and chip defects in locations that are prone to it. Okay. So I mentioned that verticillium can contribute to stem and chip defect formation. I'll just show a little data here. We're looking at plants from experimental plots that were either fumigated or not fumigated, where we grew 3 different chipping potato varieties: Snowden, Frito-Lay 1879, and Frito-Lay 2053. And we're comparing the chips with defect scores of 3 or greater in early season, during the growing season, when almost nobody shows defects to speak of; late season, where we start to see some defects in the 1879s from the non-fumigated field; at harvest, and then 2 months in storage, where, again, defects are showing up now much later at harvest and throughout storage, but they're more prominent in the non-fumigated field than in the fumigated field, and in the samples that tested positive for verticillium rather than the ones that didn't. So what is verticillium doing in this case? I don't think we have a solid answer for that. It could be contributing to loss of canopy and thus increase in soil temperature. It could be interfering with water relations of the plant and that adding an additional stress. No one has data that suggests definitively one way or another. All right. So what can you do to manage stem and chip defect? Resistant varieties are the best option if that's an option for you under whatever contract or growing situation you have. Because it can be triggered by multiple environmental factors, it's difficult to control the causes. The best thing you can do is, as Mike already alluded, for sugar and defects, is if you can use a more resistant variety, and then good growing practices. So I showed you some data earlier about how heat stress can cause stem and chip defects. This is the variety Manistee under exactly those same conditions. The control varieties that didn't receive the heat stress and the control treatment that didn't receive the heat stress, and another replicate that did receive the heat stress. This is 1 month after harvest. And you can see how beautiful the chips are in both cases. So the difference between a susceptible and a resistant variety can be quite large. Manistee is one that we have found that works, that is fairly resistant. Another, that more recent variety that we're interested in is Niagara, just recently released from Cornell. Similar situation, very resistant to defect formation, at least following heat stress. But I will emphasize that both of these varieties in a field situation can develop stem and chip defects. They're not immune, they're just more resistant. Okay. Other varieties, I'll just go back. Other varieties that we've seen some good performance from, a couple of older varieties, Nicolay and Pike, varieties to avoid. Atlantic gets beautiful stem and chip defects if you put it into storage. I think it's one of the reasons we don't want to store Atlantic. Mega Chip was one that looked kind of promising out of the Wisconsin program, but it became the poster child for stem and chip defects. Snowden, as I've mentioned, is moderately resistant, but not particularly so. Lamoka may be a little better, but again, you can see pretty nice defects with that one too. So the choices are limited, but there are at least some choices that give you some good options. Okay, additional management options. Everything that Mike talked about in terms of root development, appropriate vine development, and avoiding early senescence applies. All these things that fall under the big umbrella of good management practices are likely to help with stem and chip defect development or preventing it. Maintain a full canopy to keep the soil shaded, to keep soil temperature down. Minimize the time the potatoes sit under dead vines. Again, that helps you to minimize heat stress to the tubers. In our production area in central Wisconsin, almost invariably the warmest soil temperatures show up around the first week of September after the vines are down, but it's still, we get a warm day and bright sun and sandy soil. Maintain soil moisture after vine kill can help to avoid temperature spikes by keeping some moisture in the soil. And then when potatoes go in, storage, use best practices for chipping potatoes. Give them adequate preconditioning time to allow the sugars to stabilize, ramp very slowly, monitor your sugars as you're ramping. Don't push storage temperature prematurely. Keep checking every half degree or as you bring down to make sure sugars aren't coming up, especially the sucrose isn't coming up. And you should be okay most times. Okay, so as for sugar end defects, stem end defects are a consequence of elevated reducing sugars. It's the reducing sugars that cause the dark pigmentation. And the reducing sugars respond to the extent of stress. I'm just showing here, remember we talked about how as you go from no days of stress to 14 days of stress, of heat stress, the incidence of defects goes up. Here we're looking at sugars under the same condition, in this case the glucose content. The difference between 0 days of heat stress and 3 days of heat stress is actually fairly small. If we look at it at harvest or 1, 2, or 3 months after harvest, we do see a very typical response where 1 month after harvest, the very end, the tissue at the very end of the potato shows an increase in glucose and that comes back down so that by 3 months, it's almost where we started from. But then when we look at the 7 days or the 14 days of heat stress, we see the same pattern. Sugars go up at 1 month and start to drift down at 2 and 3 months, but they don't get down nearly as far in that time frame, and it's not clear from this that they're ever going to get to acceptable levels. So, if you want to solve the stem and chip defect problem, you should just prevent reducing sugars from accumulating, right? Well, maybe you can't, right? So the reducing sugars are produced by an enzyme. The enzyme is acid invertase that cuts the sucrose molecule in half and produces 1 molecule of glucose and 1 molecule of fructose, and those are the reducing sugars. And then during cooking, those react as part of the cooking process to produce light-colored, beautiful chips and good flavor if there are not too many reducing sugars, and dark color and off flavors if there are too many. So we can use molecular biology to suppress the activity of the invertase gene and have less invertase enzyme. And that is one method for reducing the severity of stem and chip defects. So in this slide, we're looking at a control, chips from a control plant. In this case, the variety is Mega Chip. And on the right, chips from plant where the invertase gene has been suppressed, so the invertase enzyme is less abundant, and you can see the chips get cleaned up actually pretty nicely. This methodology has actually been commercialized by Simplot Plant Sciences and their biotech potatoes. And I'll just point out that the same approach works, same cause is what causes sugar end defects, as Mike mentioned, right? This accumulation of the glucose at the stem end that causes the dark coloring. And if you suppress the enzyme using biotechnology, you can see this difference between Ranger russet in this case. On the left, that has the regular Ranger russet. You see a fair amount of dark ends and actually some dark fries overall. And then the low invertase Ranger russet, where the fry sample has been cleaned up substantially under the same conditions. Okay, so we're getting to the point where it's time to wrap up, so I'll go with this summary. Stem and chip defect occurs erratically in many areas, especially in the United States. It's tended to be in the eastern half of the country. Defects are caused by in-season stress. The timing of that stress, I didn't mention this before, I should. The timing is not critical. We've been able to impose stresses early or late and still see defects formed. Reducing sugars are elevated at the defect site, specifically right where the dark pigmentation shows up. And that's relevant because if you juice an entire potato and measure sugars, the dilution factor of the rest of the pristine potato may mask the fact that you actually have elevated reducing sugars. Varieties differ in their susceptibility to defect formation, and variety choice is one of the better ways of reducing the amount of defects in a chip sample. Defects may become less severe in storage. That's something to hope for. In-season and storage medicine practices that promote low sugars will minimize defect severity. I think that everyone who's growing chipping potatoes is trying to do this anyway. Sugars are always going to be important. And then finally, biotech potatoes with low invertase activity are one way to reduce defects, but may not be a way that works for you or your customers at the moment. So with that, I'll turn it back to Carrie and see what she has to say.
Well, thanks so much, Paul. That was an excellent presentation. For our audience, if you haven't already done so, please type your questions or comments into the chat box, also indicating to whom the question or comment is directed. To start us off, here's a question for Mike. Does harvesting early reduce the impact of sugar ends in storage?
Thank you, Carrie. So basically harvesting at that physiological maturity, when the sugars are at their lowest level, starch is at the highest, the average of when that date occurs, the research at WSU has shown, is the best way to get the optimum processing quality in general, have the lowest reducing sugars, have the fewest problems with sugars in storage.
Excellent, thank you. One more question for you, Mike. If a grower were to focus on one management practice outside of variety choice to reduce the risk of sugar ends, what would you suggest they concentrate on?
I would really look at what I would call their rotation management. You know, what crop are you growing in front of the potatoes? Is it a high residue crop? And how long between potato crops, so that you're minimizing compaction, minimizing diseases, and really promoting a healthy root system, a healthy vine throughout the season.
Thank you.